So having said all of this, let's get on with week 5. Week 5 notes. Week 5 notes are under exam 2 on Blackboard. So if you go to course material, exam 2, you'll be able to find week 5 notes there. It covers sections 2.3 through 2.5.
We're starting at week 2 minutes.
So what? Yeah.
We're starting.
Yep. So to start off with, we've got what's called the product rule. I should back up a little bit. These notes are a little bit out of order, if I remember correctly. I think I go over 2.4, 2.5, and then 2.3. So if you're looking at this, and you're like, well, why did we just jump to section 2.4? It's because I took these notes out of order intentionally. So getting on with product rule, what product rule is going to let us do is say, we've got a function. Let's call it f of x. And it's equal to two other functions multiplied together. F of x times g of x. So we've seen this actually a bunch. In fact, we just saw it. An example of this would be, we have f of x equal to x plus 3. G of x is equal to x minus 2. Then f capital of x is equal to x plus 3 times the quantity x minus 2, right? Let's say we don't want to go the extra mile and FOIL this thing out. We don't want to go ahead and say, all right, x squared plus 3x, my mistake, 1x. Did I factor that the wrong way? No, that was 10%. Okay. So this is going to come out to be just x, and this is going to come out to be minus 6. So if you don't want to FOIL this out, you want to find the derivative of this though. So without having to go through this extra step of FOILing, we have what's called the product rule. The product rule, as a proof, or to prove a product rule, we're just going to hold all of this to be true, right? That our function f of x and our function g of x are both differentiable. We'll talk a little bit more about later. We're going to say, all right, find the derivative. Let's apply the limit definition first. All right, so we've got capital F of x plus delta x minus f of x, all divided by delta x. All right, well, we can break capital F of x up into lowercase f and lowercase g, right? Once we do that, we can add a 0 in here. This is where this proof gets a little tricky in some sense. Is we go from this statement of the limit as delta x goes to 0 of f of x plus delta x times g of x plus delta x minus f of x times g of x. Now, to move on to the next step, what we're going to do, we're going to add 0. We're going to choose 0 in a very particular way. I say first, 0 is equal to 0 divided by delta x, right? Do I agree? So now, if we go ahead and represent it by breaking up our f of x and our g of x this way, so say is f of x plus delta x. So let me keep with the way I'm writing everything. F of x plus delta x times g of x minus f of x plus delta x g of x divided by delta x. This is still 0, right? Just representing it in a very particular way. So we're going to add this term into here. So it doesn't change anything. That's what we're doing right here. That's what this whole thing is about. Now, notice what this lets us do now is break up our fraction here, right? We can break it up so that one term is in terms of the derivative of g. The other term is in terms of the derivative of f. Everybody do this? So if that's the case, then what we're going to give is f of x plus delta x times the derivative of g plus g of x times the derivative of f. Well, now we have a rule to handle this. We've already seen it a couple of times. The sum and difference rule for the limits, right? And then we can distribute that limit to our two unique terms or our two unique factors in both terms, right? So we're going to distribute that limit to our f of x plus delta x, and then to what will eventually be our derivative of g. And then again to our g of x, and what will eventually be the derivative of f. That's what we see here. In the end, it all reduces down to one nice final statement that says the derivative of f of x times g of x is equal to g of x times the derivative of f of x plus f of x times the derivative of g of x. This is the product rule. So just to help show everything. G okay, so granted, it doesn't look like it would be that useful or that helpful, right? Like foiling is pretty quick, and once we foil it, we just apply the derivative directly onto it. So why would we want to do this? Well, it's because you can't always actually FOIL something out. What if we had a trig function in here? We're not going to talk about trig functions in this class, but we could imagine a case where we want to take the derivative of something like can't FOIL that out. So you're going to have the product. That's why we have it. Because FOILing is not always an option. Sometimes, frankly, FOILing isn't that convenient. What if we had something that was like 3 terms long times something that's like 4 terms long? I have a shit ton of terms, right? Like A plus B plus C plus D times E plus F plus G. FOIL that out. Don't want to, right? Feel a lot quicker just to go ahead and apply the product rule. So this is why we have it, is sometimes it's just more convenient than actually FOILing things out. And sometimes you just can't FOIL things out. So when FOIL is foiled, hey, pun. Okay, I'm sorry, no more dad jokes. So, getting back to the point of all of this, the product rule. The derivative, the product of 2 functions, f of x, g of x, is equal to 1 function differentiated times the other function, plus the other function differentiated times that undifferentiated function, the remaining function. Is everybody cool with that? Folks at home, how well can you hear me, just to make sure?
We can hear you fine.
You can hear me?
Yeah, you're good.
Awesome. Huh. All right, so we've got this idea of the product rule. Now let's use it. All right. Let's go ahead and apply it to this. First, we need to identify what our f of x and our g of x will be. F of x will be that first set of terms, right? That first factor. So it's going to be 3x minus 2x squared. That's convenient. Let's go ahead and just stick with that. G of x is going to be equal to 5 plus 4x. All right. What's the derivative of f of x? It's going to be pretty quick to find, isn't it? Just going to be 3 minus 4x. And the derivative of g of x, well, that's just going to be 4. So, to answer the question, what is this derivative? Well, this is just going to be g of x times the derivative of f of x plus f of x times the derivative of g of x. We already found those derivatives. Plugging all of these in now. G of x is just 5 plus 4x. This derivative of f of x, well, that's just 3 minus 4x. f of x, well, that was just 3x minus 2x squared. And the derivative of g of x, said that was 4. Now we could FOIL this the rest of the way out if we really wanted to. If we wanted to. I don't think we want to.
So how did you get 3 minus 4 and 1?
So the derivative of a constant, that's 0, right? And the derivative of 4x using the power rule, it's just going to end up being 1, isn't it? Because we pull the constant outside, lower the power on x by 1, and bring down the original power. Agreed? So it would look like this. Dx of 5 plus 4x is equal to dx of 5 plus dx of 4x derivative of a constant is equal to 0. Constant multiple rule says we can pull out that 4. Right? And now, our rule says this is going to be 4 times 1 x to the 1 minus 1. One times x to the 1 minus 1, which is just equal to 4. You can think of rewriting this with the power up top, right? We can sneak in that 1 right there.
So would this on the right be our final answer, or would we want to push it down a bit more?
It depends how the problem read, right? Like how it's written. If it asks you to simplify it, go ahead and bust it the rest of the way out. If it doesn't, this should be good, but if it doesn't accept it, it should expand it out further. Just kind of depends on the situation. I know that's not exactly a satisfying answer. In our case, it does want us to expand on it.
Or just flip flop
Yeah,
from like where it is, but that shouldn't matter. Because we're just having it.
because we're just adding everything, doesn't matter here. So like I said, here they do go ahead and expand everything. Or simplify everything as much as they can. Which is just a good practice. Like it is something we should do automatically anyhow. are individual variables. So looking at another example, let's say we have the function 1 over x plus 1, that quantity times x minus 1. Well, taking the derivative of each individual part, right, and just putting it back together, you run through it as if it's almost algebra at that point. Agree? So first, go ahead and rewrite everything in terms of powers. Just because product rule is a lot easier to see, understand, and apply when you do that. So after you rewrite everything in terms of powers, go ahead and find each individual function, define each individual function, f of x and g of x. So what I am saying is, start off by saying, all right, cool, my function f of x is equal to 1 over x plus 1 times the quantity x minus 1. I'm going to go ahead and rewrite this. Wait, this capital F. No, they used F, so we'll use F. Go ahead and rewrite this in terms of powers. So this is x to the negative first plus 1. That quantity times x to the first minus 1. Now, we're going to declare a g of x. Let's have that be x to the first factor here, x to the negative first plus 1. Now let's declare another one. Well, this h of x. That's going to be x plus 1.
Is plus 1 or is it minus 1?
Minus 1, my mistake, you're right, you're right. You are correct. So now we can take the derivative of each of these, just plug it back together after that. And that's the entire process of that, to this. Start by rewriting, then declare what your individual functions are, take the derivatives, put it all back together. Everybody cool with that? Yeah. So I'm going to give y'all, let's say 5 minutes to do A. I want y'all to use the product rule. I'm going to boil it out. We should end up at the same place. So I went ahead and did the, both the product, I applied both the product rule and I went ahead and boiled it out. That said, I went about the product rule probably a little bit different than what y'all might have. I went ahead and factored out an X up here. Just because we had an X in both terms, putting an X here didn't hurt anything, but it did turn this derivative to 1, which made the math down the road a little bit easier. So really quickly, looking at the way the book went about this. The book says, okay, first, let's define g of x to be our x squared, right? My mistake, to be our 2x. Then let's define h of x to be our x squared plus 3x. So when we put all of this together, we have g of x times the derivative of h of x plus h of x times the derivative of g of x. So this is doing that. The derivative of h of x would be 2x plus 3. The derivative of g of x would be 2. So distributing and dropping our parentheses, we get. And now just cleaning up all the math, we get 6x squared plus 12x. Now let's compare that with what I just did. I factored out this x up here, and I grouped it with our 2x. So we have 2x squared times the quantity x plus 3. Okay, so let's set g of x equal to 2x squared. Then its derivative is going to be 4x. Let's set h of x equal to x plus 3. Well, then this derivative is going to be 1. Now applying the product rule, we're going to have the derivative of one of the functions times the other, plus the other, plus that first derivative, that first function times the derivative of the other function. Which is what we got here, right? Derivative, one of the functions times the other function. Derivative of that first function times the other, right? Makes sense what I mean? So going through and distributing everything, here we're going to get 2x squared plus 4 times x, that's going to be 4x squared, plus 3 times 4x, it's going to be 12x. That gives us to right here. And then we simplify everything. Get it all up. Now comparing that to the FOIL method, I went ahead and distributed out 2x to each of our terms in the second factor, right? So, all right, 2x times x squared, that's 2x cubed, plus 2x times 3x, it's going to be 6x squared. Take the derivative of this. Well, we can pull out that constant multiple rule, right? Pull out this constant, same rule. Now, from here to here, we're just applying the power rule. So if everybody remembers, power rule says the derivative of x to the n power is equal to n times x raised to the n minus 1 power. So applying the power rule here, applying it here, we're going to get 2x times the factor 3x squared plus 6 times the factor 2x. simplifying everything, we're gonna get 6x squared here, 12x here. And I went ahead and just pulled out the 6x. So doesn't matter, as long as we follow the rules of calculus, we're gonna always get the same answer. Or at least we should, because if we don't, something bad happened in math. That generally is true, I should say. There are other cases in like trig where totally different looking functions will actually be totally equivalent to each other. Luckily, we don't have to deal with trig functions in this class. But like I said, as long as we apply the rules correctly, we're going to get the right answers. Doesn't matter how we apply them, as long as we apply them correctly. That said, we could go beyond just 2 factors. Let's say we wanted 3 factors here. So we wanted 4 factors, 5 factors, 6 factors. Now I point this out because, all right, boiling out 2 terms, or 2 factors, that's not that bad, right? When you have x plus 3, that quantity times x minus 4, that quantity times x squared plus 6x plus 12, now things start getting messy, right? Who wants to go through and actually boil all of that out, expand it out, figure out what that polynomial is, and then take the derivative? Nobody has time for that. So, product rule to the rescue. Get this. This brings us to what's called, what is called the quotient rule. And the quotient rule, to prove, it's pretty much the same proof. I shouldn't say pretty much the same proof. It uses the same trick as the product rule. We add a 0 right here. But instead of f of x plus delta x, now we're going to use f of x. In what this whole thing is doing, step by step. First, we're saying apply the limit definition of the derivative, right? And rewrite your function as the quotient of 2 other functions. All right. Once we do that, notice we can rewrite this using algebra, right? So what we're going to do here, once I get this erased, we're going to take f of x plus delta x divided by g of x plus delta x minus f of x divided by g of x, all that divided by delta x, multiplied by 1. Just because it'll be easier to read this, I'm going to rewrite this again, slightly different this time, or rather in color. F of x plus delta x g of x plus delta x, g of x. Subtract this. Okay. What we want to do is we want to get rid of the fractions in our numerator. So to do that, we're going to multiply by 1. We're going to choose our 1 in a way that cancels out or kills off those fractions. We're going to use the 1 g of x plus delta x times g of x divided by g of x plus delta x times g of x. So what happens here is we have f of x plus delta x divided by g of x plus delta x all of that being multiplied by g of x plus delta x times g of x minus f of x divided by g of x plus delta x times g of x all of that divided by delta x times g of x plus delta x times g of x. Holy shit, that was a lot. Okay. Notice right away we've got some cancellations, don't we? This term is going to cancel with that. And this g of x is going to cancel with that g of x. So what we're left with is f of x plus delta x times g of x minus f of x times g of x plus delta x, all that divided by delta x times g of x plus delta x times g of x. Now all of this is just to get us to here. From here to here, we're just adding 0. Now we're going to say, well, this thing plus f of x, g of x, minus f of x, g of x, divided by delta x times g of x plus delta x times g of x. Because this thing's 0 right here, right? Because f of x times g of x minus f of x times g of x in the numerator is 0. 0 divided by anything is still 0. So this green term here is just 0. And that's where this comes in. Then they say, all right, we can break this up. We break this up. We're going to bring up delta x and break up our fractions. Then we're going to have this g of x times g of x plus delta x pulled off to the side as another factor. Well, notice this thing isn't really going to change, right? It's going to go ahead as delta x goes to 0, it's going to become g of x squared. What you get up top in your left term, it's just going to be g of x times the derivative of f of x, minus f of x times the derivative of g of x. All of that divided by g of x squared. So this entire proof takes a couple tricks, and it is long and arduous. But walking through it, the real trick, like I said, to multiply first by 1, choosing the right one. And then after your cancellations and rewriting everything, adding 0. From that point, you're just collecting terms. You're saying, all right, part of this looks like a derivative of f. Another part of this looks like the negative of the derivative of g. Taking care of all that, grouping it all together, the rest of the proof follows. Cool. So all this is just to say that the derivative of two functions divided by each other, right? So f of x divided by g of x. The derivative of that is g of x times the derivative of f minus f times the derivative of g divided by g squared. We have to assume, though, that g isn't equal to 0, because we can't put 0 in the denominator, right? And 0 squared is still 0. All right, how the hell are we going to remember this? Remember it with this great mnemonic, low d high minus high d low over the square root of what's below. In other words, looking at what you started with, we've got low g of x, d high, f prime of x, minus high f of x, d low, the derivative of g of x, so g prime, divided by the square of what's below, g of x squared. This is the quotient rule. That said, as we go through the rest of the semester, we're going to learn a few other differentiation techniques that make it so you don't have to necessarily worry about g of x, and it's when you're really convenient. In fact, the chain rule will get you around this very quickly. Because what we really have is f of x times g of x. Move on, right? So after a while, we're going to see the chain rule. That's going to make it a lot quicker to solve this without necessarily knowing the quotient rule. That said, know the quotient rule. it's good to know sometimes, as opposed to having to use the chain rule. So we'll see this. All right, so let's say the derivative of this crazy beast. First, f of x f of x is what's on top. That's x minus 1. G of x, that's what's down below. So that's going to be 2 of x, or 2x plus 3. Find the derivative. We get g prime of x is equal to just 2. And f prime of x is equal to just 1. All right, so taking the derivative now of f of x over g of x, right? d dx of x minus 1 over 2x plus 3 the mnemonic was low b high 2x plus 3, right? Low. B high, that's the derivative of what's on top. It's just 1. Minus I, that's x minus 1. D low, so it's just 2. Divided by the square of what's below. So that is 2x plus 3 squared. So all I did here was first find the derivatives of what's on top, what's below, then apply the mnemonic, right? Low b high minus high b low divided by the square of what's below. Okay. Now going ahead and doing the rest of the algebra that remains, we've got 2x plus 3 minus 2x minus 2 divided by square of this is going to be 4x squared plus 12x plus 9 distributing our negative all the way through. And dropping our parentheses, we get 2x plus 3 minus 2x plus 2 divided by 4x squared plus 12x plus 9, or 5 divided by 4x squared plus 12x plus 9, and that is assuming I did not make a mistake. And it looks like it did. Cool. So low d high minus high d low divided by the square root of what's below.
And they just did squares down below.
They just left it as a square. So let's see. So for whatever it's worth, we're probably going to spend like 3 or 4 weeks on just derivatives before exam 2.
Okay.
It's like there's going to be a huge gap and then exam 2, because derivatives, I personally think the way the exam should be broken up is first section covers up to limits, exam 1. Second exam covers everything with derivatives. Third exam covers everything on integrals. I shouldn't say everything. It covers the first half of integrals, and then the second half of integrals is exam 4.
And we have exam 5, which is important.
Yes, exam 5 is technically 5, if you want to think of it as exam 5.
And that's cumulative. Is the final.
Yes. Yes. So I just wanted to make this point of, don't look at this and be like, oh God, I have to know all of this by the end of next week, because exam 2 will be next. No, exam 2 is not next week. It's going to be a little lot. Like I said, probably 2 or 3 weeks of this, and then exam 2. Having said that, to find the equation of the line tangent to this function at x equal to 1, we need to apply the quotient rule here, right? Well, first, can we factor anything out? Not that I see. Nothing immediately jumps out at me. I think we can, but I'm not going to try. No, we can't. Do that. Yeah, that's not going to happen. We could use long division though, and maybe rewrite this fraction, right?
Yeah.
But for now, we're just going to apply the quotient. So what this graph looks like is Kirby's hands hugging a line, right? Kind of. Anybody, Kirby? Okay. Folks at home, if you didn't laugh at that, I am failing you.
Kirby's the fat thing,
It
right?
was cute.
I'm failing you for asking that question. All right, so what we want to do is find this line. This is the line tangent to our graph at x is equal to 1. So what we're going to do, we're going to apply the quotient rule. That's going to give us the equation that lets us find the slope of our tangent line, right? So, low d high minus high d low divided by the square root of below. Then run through a bunch of algebra. If we get done with all of that algebra, we get to here. This is the equation that gives us the slope of our tangent line, right? So what we're going to do here is we're going to say, all right, erasing all this, d dx of, that was 2x squared minus 4x plus 3 divided by 2 minus 3x. That thing is equal to negative 6x squared plus 8x plus 1 divided by 2 minus 3x, that quantity squared. Okay. Now I'm going to write something weird here. And I want you all to roll with it for a second. Let's call this n of x. What I mean by this is the function that gives the slopes of our tangent line, right? So let's just call it n of x. All we did was take the derivative. Now we're going to say, all right, tangent line at x equal to 1 has slope d dx of our function 2x squared minus 4x plus 3 divided by 2 minus 3x at x equal to 1, right? So that's just going to be equal to n at 1. So we're going to plug 1 into this, is what I'm saying. Everybody cool with that? So this is going to be equal to negative 6 times 1 squared plus 8 times 1 plus 1 divided by 2 minus 3 times 1, that quantity squared. That's going to be our slope. Yeah? Because the slope of the tangent line is equal to the derivative of your function at that x value. Yeah. So now we're going to come over here and say, all right, cool. We've got a way of finding m now. M is equal to, this is going to come out to be 6, that is 2, that is 3. So down here, this is going to be negative 1 squared, so it should be 3. Is that right? Is that what it says? Yes. Slope is 3. Cool. Now, the next thing we need to know is what our x, y values are. We know x is 1, and we know y is going to be our function evaluated at 1, right? Okay. So plugging that in, coming over here. No, coming over here instead. This is going to be plugging 1 in, that is 2 minus 4, that's negative 2, plus 3 is negative 1. I mean, my mistake is 1 divided by 2 minus 3x. So 1 divided by negative 1 is going to give us negative 1. Right? So this is our point of concern. Now, the line, tangent line of X is going to be found by putting all this through point slope form. Agreed? If you're shaking my head, my back is to you, so I can't hear it. Agreed? Just gonna put it through point slope form now to find that tangent line. Let's say, all right, cool. Point slope form tells us we've got y minus -1 is equal to m is 3 times x minus 1 . So this is going to be y plus 1 is equal to 3x minus 3. Subtracting 1 from both sides. Y is equal to 3x minus 4.
So where does that n equals 3 come from?
It came from the fact that the slope of our tangent line has to be equal to our derivative at x is equal to 1. So we said, all right, find the derivative, that was this. Now set x equal to 1. That is the slope of our tangent line. Because the tangent line has slope equal to your derivative, right? That's the definition of what the derivative is. It is the slope of the tangent line. Everybody cool with that? So because the derivative is equal to the slope of the tangent line, what you're trying to do is find the line tangent to your function at x equal to 1, then the slope of the tangent line is going to be the derivative evaluated at x equal to 1, which is where we got 3 from. Putting 1 through all of this.
Okay, so then you just did -1 since you have one.
Then I said our x naught, y naught has to be on our function, right? So we want to find the tangent line at x equal to 1. Well, that means we automatically know 1 point on our tangent line. It's going to be the line, or I mean, it's going to be the point 1, or whatever your function evaluates to be at 1, which was -1. So 1, -1 has to be in your tangent line, because your tangent line touches your function at exactly that spot.
So if it was at 2, it would be -2.
If it was at x equal to 2, it'd be whatever the original function evaluates out to be at 2.
Okay.
And then we would also have to go back to this and say, instead of 1, plug in 2. Make sense? So this is going to be equal to whatever your derivative evaluates out to be at the ascribed x or y value. Right? These are going to be the one and only points that your tangent line touches your function at. So at that ascribed point. And then from there, to get the line, or the equation of the line, you use point slope form and solve for slope intercept. Cool. watching a lot of Community lately. It's kind of my spirit animal.
Of course.
What does that mean? Of course.
No.
Wow. I feel like I just like,
I thought you liked Ovid.
I do, but of
I mean,
course.
Ovid's pretty great.
Right, that's what you meant by that. All right, so I think here we can take a break since we started about 30 minutes into class after having gone over a couple problems. So let's go ahead and take a break. 10, 15 minute, or 10-minute break, 10-minute break, not 10 or 15, 10, 10.
Ten.
Yes,
Exactly 10.
yes, exactly 10.